So yesterday we looked at chord/arc theorems. Let's have a look at some of the angle theorems to start off with. And we talked about that yesterday when we were defining subtend. So there it is. The angle subtended by an arc, again you could insert the word chord there, at the centre is double the angle subtended by the arc at the circumference. It is better to say arc in this case than chord though. And I'll explain when I get the diagram there. So if I was going to use that idea, well then that's what I'd write. Angle at the centre, twice the angle at the circumference. But it is important, those last three words, on the same arc. Now the reason we say arc rather than chord, if I wrote chord AC, yes it's true that chord is subtending, but there's two directions I could go with a chord. Where when we say arc, there's only one direction I can go. So it's very clear which way the angle is going. So that's why it's better to use arc rather than chord. All right, let's prove it. Let's prove the angle at the centre is indeed twice the angle at the circumference. So I'm going to draw in, well, a bit of the diameter there coming from B. I don't really need it to go all the way. We know triangle AOB is isosceles. So we've got two equal radii there. It's got to be an isosceles triangle. So if that's true, then OBA and OAB are equal. I've used the terminology that people tend to frown on there. Base angles of an isosceles triangle. People tend to write equal angles of an isosceles triangle rather than that. But now AOX is the exterior angle of triangle AOB. So it'll be OBA and OAB added together, but we've just said they're equal. So I could say AOX is twice angle OBA. Now, that's when I did everything on the left-hand side of the diameter. I could have easily done it on the right-hand side. So I'm not going to do the whole thing again. Angle COX will be twice OBC using a similar method. If you're now going to prove something which is basically exactly the same proof, but using different angles and what have you, but the actual technique is identical. Had I gone and proven COX is equal to 2ABC, I would have done exactly the same thing. I would have said triangle OBC is isosceles, and then I would have said, oh, therefore OBC is equal to OCB, and then I would have gone, well, therefore COX is equal to, and so it would have been exactly the same steps, just with different angles. So it's fair enough to say, by a similar method. So it's exactly the same technique, just using different angles. And that's perfectly fine. So I've said AOX is 2OBA, COX is 2OBC. If I add them together, then I get, well, AOC is twice ABC. So there's our proof. That brings us to the angle in the semicircle is a right angle. So I can say, well, let's draw a diagram, it'll help. There we go. I can say ACB is 90, and there is no simple put. So we just write angle in a semicircle. That's a very easy proof, this one, because I'm basically just going to use the last theorem that I proved. I mean, AOB is a diameter, we know that, but I could look at it a different way and say, well, hang on, yes, it's a diameter, but it's also a straight angle. So the angle at the centre is 180 degrees. So by the last theorem we just did, well, hang on, AOB must be twice ACB, angle of circumference on the same arc. So it's got to be 90. Okay, that'll do us for today. 9.